numbers in example 2 and work this out. VBB 4 volts. Can you all draw this circuit and indicate the 4 volts? RB 100K, RC 1K, VCC 9 volts. HFE. HFE, what's HFE?
Current gain?
Is the current gain. So it's the current gain, and what does current gain, what is the equation for current gain? It is equal to IC over IB. Okay, that's the definition of the current gain. It is how big IC is compared to IB. In my case, it's given to be 125. Okay, so let's analyze this circuit. The first thing I will do is identify VCE cutoff, this point here. So what I do this time is show my graph in the third quadrant. Why third quadrant? Because the voltage is negative and the current is negative. So that's why I'm in the third quadrant. In the case of the NPN, I'm in the first quadrant. Voltage is positive and current is positive. So now what I'm going to do is take a point here, call that cutoff. Take a point here, call it saturation. Draw a straight line that connects cutoff with saturation. And let me calculate cutoff. Okay, here we go. First calculation. Cutoff. VCE cutoff is saying that the transistor is open. So if I was to replace this transistor with an open switch like this, okay, so let's show an open switch. So like this.
Praveen, could you please close the door?
Yes. So let's put a symbol of an open switch beside my VCE cutoff. If this transistor acts like an open switch, then the voltage from the collector to the emitter would be equal to the source voltage. So that's VCC, so that's 9 volts. Now, what I want you to read is the note at the top of the page which says, for the PNP circuit, do all your calculations as if it is an NPN circuit. Simply change the polarity of the voltages and currents after the calculation. So, as you can see, the direction of the currents change, the polarity of the voltages change, and we're doing a lab this week where we build this circuit and we measure all the voltages and currents, and we notice that they are of a opposite polarity. So, what I want you to do is at the edge of your page, I want you to draw a dotted line like this and indicate actual, and in this case, write down negative 9 volts. So VCE cutoff is negative 9 volts, and what I'm going to show then is the negative 9 volts on my graph. Put a 0 to identify where the two axes intersect and indicate negative 9 volts here. So that's my cutoff point. That's where the transistor acts like an open switch. Now, let's do the second calculation. IC saturation. That's the other extreme point, right here. That's when I replace this guy with a closed switch. If I was to replace the transistor with a closed switch, I've got a voltage and I've got a resistor. And it's a simple circuit made up of a voltage and a resistor. So what would be the current in this circuit? It would be V over R. So IC sat, let's show a symbol of a closed switch. So that's VCC over RC, which is 9 volts divided by 1K. How much? 9 milliamps. Because the direction of my current is opposite to the NPN, I indicate the actual value after the dotted line, negative 9 milliamps. Okay? So that's IC sat. Let me show the value of negative 9 milliamps on the graph right here. Now, we find the operating point of this circuit. So, if I want to determine, is it operating somewhere here, close to the middle, down here, or down here? We don't know. We have to find out. But it will be operating somewhere on the DC load line. The operating point is always somewhere on the DC load line. And the way to find that value is 3 steps. The 3 steps are, first find IB, then find IC, and then find VCE. 3-step process, okay? IB.